welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about an interesting classifier, and a simple one, which is called Nearest Neighbours. We actually start by nearest neighbor algorithm for classification, then we will extend that to nearest neighbors. Okay, so what is nearest neighbor? It is a non-parametric method for classification. So it is non-parametric. So what does it mean? If you remember that if we have some data like this, then for this data we could actually train a linear classifier such as SVM to derive this decision boundary. Okay, so we call this classifier a linear classifier, okay, because the decision boundary is a linear hyperplane. Okay, so in other words, we could say that the decision boundary is, this is the equation of decision boundary. Okay, it is a linear equation. Okay, and so this is a parametric model because this model has some parameters which are W's and W null, and these are the parameters of the classifier. But KNN is non-parametric method, means that it doesn't have any parameter in that. And also the decision boundary of nearest neighbor is nonlinear. In fact, it could be nonlinear. Okay, and so alternative to parametric models are non-parametric models. Thus we generally have two category for classifiers. The first one is parametric models, and the second one is non-parametric models. Okay, and what we learned about SVM, logistic regression, and so on, they are parametric models because they have some parameters. But NN and instance-based methods, some of them are non-parametric methods. Okay, so we call this actually instance-based learning. So non-parametric actually methods typically are simple methods for approximating discrete value. It means that they are used for classification, or real valued actually target functions. In here we will talk about classification, but for nearest neighbors, but you could actually extend it for regression, and you could use that for regression task. Okay, so in KNN or in NN, learning comes to simply storing training data. So for training the models means that you need just to store the training data because you don't have any parameter to learn. Okay, and test instances, when you have a new data that you want to classify, test instances classified using similar training data or training instances. So you search for similar training instances for your test data, and then you classify your test data. So in here we have two underlying assumptions that you should know to these two conditions. The first one is that the first assumption is that output varies smoothly with the input. So we have smooth variation of the output regarding to the input. Okay, and the second one is data occupies subspace of high dimensional input space. Okay, so if you have a very high dimensional data, it assumes that the data subspace is actually has some lower dimension than that high dimensional space. Okay, so now we want to talk about specifically about the nearest neighbors. So let's say training example are in Euclidean space. So we have a d-dimensional vector for each data. Okay, so the idea is to the value of target function for a new query or for a test data is estimated from the known value of the nearest training examples. Okay, so for Euclidean space, we know that the distance is between two points. XA and XB is the root square of sum over all dimensions difference squared. Okay, so we know that for this is true in Euclidean space. Okay, so now we could build the algorithm of NN or nearest neighbor. So sometimes it's called 1NN. We will tell that why. Okay, so it is pretty simple. First, you should find example X star and T star that is closest to the test data. Let's call it X. So in other words, we want to, the X star is the argument or minimum argument of for all xi's in training data, we want to find the minimum distance data with the test data, which is X. Okay, and after finding this, which is now we know what is X star and what is the value of that. For example, it could be X star with the class 1 or with class 2. Then for the output value of the test data, we could return T star, which is the output value of X star. Okay, so in this space, if it is pretty simple. It says that if you have something like this, now you have a new test data. Let's say here you have a data, or making it more realistic. Let's say this is shoe size, and this is let's say 8. Then we could actually let's say these data are related to women's, and these data are related to men's. And now we know a new shoe size and a height, and now we want to know whether this data is woman or man. Okay, let me show that we have triangle in here. Okay, for this, if you want to use the nearest neighbor, it says that you should calculate the distance between all of these and the test data and all of the training examples. Then you should select the nearest point in here, which is this one, and return the output value, return the class of the nearest neighbor as your output. So in this case, we say that the output value for this test data is man, the label, because the nearest point is actually a man, okay, in Euclidean space. Okay, so this is a real simple algorithm which has some advantages and disadvantages. One of the issue, or not generally, it is not an issue maybe. So one of the properties of NN is that it does not explicitly compute decision boundaries. Okay, so it is not like SVM. So because in SVM, for example, we know that the classifier is parametric, and we could derive the decision boundary explicitly from the equation. But in KNN, or in nearest neighbor, we don't know what is the exact decision boundary equation. But actually we can infer that, okay? We call it Voronoi diagram visualization, okay? So it actually shows how input space divided into classes, and each segment is equidistance between 2 points of the opposite classes. So let's say an example of Voronoi diagram, and then for nearest neighbor to get some intuition about it. Okay, this is good, I think. For example, in here, okay, this is, yeah. In here, you could say that, okay, this is the decision boundary actually. So if you have a data point in here, it means that you the class of test data belongs to red data, and if you have a data in here, your test data belongs to blue class. Okay, and these are actually the segments that if you have a point in here, means that the nearest neighbor of that point is this data. Okay, if you have a data point in here, means that the nearest neighbor of that data is this data point. Okay, so now you know what is Voronoi diagram. Okay, another property of NN is that actually it is an advantage, so it can work with modal data, with multimodal data. So if you have two classes data like this, let's say this is the first class, so these are the data points of first class, and the second class is data points are in here, here. So you know that the classification for example SVM in this case is actually kind of hard, but for nearest neighbor, now if you have a data point in here, it knows that it is from this class. If you have a data point in here, it knows that it belongs to red data, and so on. So it could handle multimodal data. Okay, a disadvantage of NN, or nearest neighbor, is that it is sensitive to mislabeled data. Sensitive to mislabeled data. Okay, or actually class noise, we call it. Okay, so if you have something like this, let's say we have the exact same thing as data in here. Now let's say because of noise or because of class noise, actually as training example we have red in here instead of blue. It is actually because of noise, or this could be outlier. Okay, now if we have a new test data in here, then we will classify that as the red samples, but we actually know that it is from the blue class. Okay, so this is one disadvantage of nearest neighbor. So what is the solution? Could we actually mitigate this problem? Yes, the answer is actually yes. We could actually smooth the output by having k nearest neighbors. So we use the voting scheme between k nearest neighbors to get the output. So in this case, if you use one nearest neighbor, so you need to just find one nearest data point to your test data point. Let's say the test data point in here, and so if we use nearest neighbor in this case, but we have, let's say we have noise training data in here which is mislabeled, this is from this class, then we will probably let me make it. Okay, now if you want to calculate the class for this instance, for this test data, the nearest neighbor of this is this data. Then as you could see, now we have a mislabeled test data. Okay, but we could clearly say that this data belongs to this class, okay, not this class. Okay, so this is the problem of nearest neighbor. So let's say we use 3NN. Okay, instead of 1 and n, again the same case, but now, so this is test data, this is noise labeled data. Now if we use 3 and n, so we should actually first calculate the 3 closest point to the test data point, which is this one, and probably maybe this one. Okay, now we should vote between the output labels. So for the output labels, we know that 2 of them belongs to this class, and 1 of them belong to this class. Okay, so after voting, we could say that the predicted class, if we use 3 nearest neighbors, is this X class, which is the right one. Okay, so if we use more than one so in general we call it K nearest neighbors, and you should calculate K nearest neighbor for a point to make the decision. So in here we solve this sensitivity to noise of label. Okay, so for general KNN algorithm, we could say that we should find K examples Xi and Ti closest to the test instance X, then the second step is classification, output using majority label. Okay, so after that we use the voting for the classification of test data. So it is the KNN. Okay, but so the question is actually, how should we choose K? If we use actually large K, it may lead to better performance, as we have seen in some cases it could robust the algorithm to the noise labels and noise data. Okay, so it could actually boost the performance. But if we use very large K, then maybe it may end up looking at samples that are not really neighbors. Okay, so in other words, far away from query. Okay, let's say in this example, if we use very large K, then it will consider probably these instances. Okay, so this is not good. So very large K is also not good. So the best way to find K is to use cross-validation. Okay, so you just need to run a cross-validation to find K for K nearest neighbor. For example, you could use 5-fold cross-validation or n-fold cross-validation to select the suitable K. But there is actually a rule of thumb to set the K. That rule of thumb is that the K should be less than the square root of n, in which n is the training. In fact, it is number of training examples. Okay, so this is actually the rule of thumb that you could use. You could verify that your k is suitable or not. Okay, what are the issues of k and n? The first issue is that if some attributes have larger range, they are treated as more important. So scaling is so important. The remedy or the cure for this issue is to use normalized scale. Okay, so it is very important to normalize the scale. So simple option could be linearly scale the range for each feature to be in a specific range. For example, you could actually set the feature range to be in the range of 0 and 1. Okay, and the second option that we could use, and it is actually advantageous, is that we could linearly scale each dimension to have 0 mean and unit variance. So it is good to apply this transformation or standardize data. Okay, so KNN is actually sensitive to the scale of features and data because it uses the distances. So it is actually makes sense to have this issue. The second issue is the complexity. Okay, so at the test time, it actually should use if we have some training data, then we have a test data. In the test time, we should calculate all of the distances between test data and all of the training examples. The computational complexity is kdn. So the d is the number of dimensions, n is the number of training data, and k is the k in nearest neighbor. Okay, so this is actually makes the test time a little hard, and so as you could see, the computational complexity is a little hard in here. So but there are some remedies for these issues. For example, for the complexity, we could use a subset of dimensions instead of using all of the dimensions. So we could reduce the d in here. Or the second thing is that we could pre-sort training examples to know that when we have a data, don't actually compute the distance with all of the training examples. We just use some of the data because we pre-sorted them. The third thing is that compute only approximate distance instead of very accurate distances, and remove redundant data. So if, for example, in this case, if we have something like this or this one, this could be probably redundant data. Okay. So if we have actually lots of samples, KNN typically works very well. So you should try that out. If you have lots of data, then you should probably try KNN. Okay, and so in general now we know the problems of KNN. To summarize, it is sensitive to class noise, it is sensitive to scales of attributes, and scales linearly with the number of examples, the computational complexity at the test time. So maybe if you have, if for you it is very important to have a fast classifier, but you have a large training data, maybe it is not, maybe the KNN is not the best suit for you. But if you use actually Scalearn and other packages, they are actually optimized the KNN so much to reduce the computational complexity, as we talked about the remedies in here. So let's see the example of KNN in Scalearn. So as you could see, the most important parameter is number of neighbors. So it is the K actually. So by default, the Scalearn use 5. And actually another important thing that I should mention is that the metric. So in here we talked about Euclidean space, and we use the Euclidean distance as a distance metric, but actually we could use another metrics to calculate the nearest neighbors, and we could have different metrics. So in here you could one of the most famous metrics is Minkowski metric. So you could use that actually, and you could actually read about it online. It is not actually related to the KNN, but it is in the metric. Okay, so as you could see in here, you could pretty straightforward use KNN classifier. And as I said, the most important parameter maybe is number of neighbors. Also, if you maybe you want to try another thing, is that changing the metric is also could be very important sometimes. Okay, let me to check for, yeah, this is good for see the decision boundary of nearest neighbor classification. Okay, in here you could actually see the decision boundary of nearest neighbor. Okay, so it is pretty good classifier, and also a simple classifier that you could use. And you could actually see one parameter, which is weight. It is uniform, and in here we have distance. So it means that when you want to consider the data points that are near to your data, maybe you want to weight based on the distance between your data points and your test data. So in here, let me, okay, in here, if we use 3NN, maybe we want to consider these distances, okay, to affect on the final decision. Okay, so you could use actually weight equal to distance as a parameter of the nearest neighbor classification, but also you could use the uniform, which means that you just calculate the nearest neighbors, but after that you don't use the distance as the weight for your classifier. Okay, I think it is enough for this session, and now you know how to use nearest neighbor. And what is that? It actually is a simple classifier that you could use when you have large training examples, probably it is a good solution for you. Okay, see you in the next session. Bye.